impact it's a way to fly less and to have a lower impact on our environment, right? So if you look at that, so there is this logo Flying Less, which is a true community of people who are not flying. And so here, this is like the carbon footprint of Peter Kalmus in 2010, and he was postdoc, living in Los Angeles, and he did during this year 2 international flights and 6 domestic flights. And this is his carbon footprint. So you can see that flying is like 13 tons of CO2. And just to remember you that normally we should achieve only 2 tons of CO2 per person and per year. Okay, so you see that. I mean, I think that, I used to have this kind of carbon footprint. Anyway, so this webinar is very nice because the impact of a 1-hour Zoom meeting is, for me or for people with a camera on, is 1 kilogram and 40 grams if you don't have your camera on. So thanks a lot, guys. It's very nice, and that's a very good way to do that kind of seminar. Okay, so now I'm going to talk about mathematics, right? So the motivation of this work is the following. So that's crystallization of metals. So you have metals, and you want to understand what is the optimal arrangement of atoms and electrons in the metals. So that's a typical picture of layering of atoms with electrons. So of course here they are like little dots, but just to make things very clear. But yeah, so basically it's like a mass of nuclei in a sea of electrons. And so usually what you see is something periodic like that, of course. This is a very thin sheet of gold here, right? So that's what you see. Okay, so there are basically 2 models that we know pretty well, or more or less. That the two-body potential, so the classical model, you are considering points in interaction with an interaction potential phi, and you want to minimize that among the position of the point, right? So it's a two-body interaction. And you have on the other way the Thomas form. That's one example, because you can choose whatever in the DFT density functional theory things. So here it's just a Thomas family model. So it's quantum. So you have several parts. Rho is the electron density, and xi, they are the positions. And of course you have all these terms: the kinetic energy, the electron nuclei potential energy, and the nuclei electron energy. So you have a lot of things, right? And what I'm going to talk about today is something in between. So something that want to play the role of the quantum model, but with something which is more computationally computational. So here it's quite difficult to compute everything, as we know, and so in my case that will be easier. And a way to know what is a quantum or a classical crystal is something that I learned like a few years ago. It's this de Boer parameter, right? And so basically, so that's lambda star here, and that's basically this quantity where R0 is a typical interatomic distance, m is the mass and of one atom, and epsilon is an energy scale from the interaction. And so once you have that, what it is said by this author is that if lambda star is larger than a certain number, which is this number, you have a quantum crystal, and otherwise the mass is too important, too big, and then you have a classical crystal, right? So for big mass, you have basically classical crystal, and otherwise you have quantum. And if I look at this picture, you have green, and so green are the classical one and red the quantum one. And so you see that for metallic system, you have both things. So it depends, of course. And the difference is not so big, right? Okay, but that's just a way to differentiate these things. And of course, for the classical crystal, you can imagine just points, right, in interaction. But for the quantum crystal, you have the electron density, which will play a role, of course. Okay, so what is the embedded atom model here? So that's what I want to tell you today. So the embedded metal model was invented by Doe and Basques in 1983, a very good year because it's the year I was born, actually. And for metallic systems, it was for metallic system, and the idea was to include a non-local electronic correction, right? So you have atoms, and you have an electronic correction that will play the role of the sea of electrons. Right? So there will be three different functions: the phi that we already know, that's the two-body potential; the capital F, which will play the role of embedded function, let's say; and rho, which will be the density of electrons. Right. So for the total energy of one system where you have n point, right? It's basically an electron contribution, which is given by the sum of F of rho I bar. So rho I bar is just interaction with rho of the point, let's say xi, with the rest, right? So there is that's an effect of the electron density. And capital F is here just to modify the the landscape, right? So it's just the way you embed everything in the system. And here, that's the nuclei contribution. That's the usual one, just the two-body potential, right? Very easy. Okay, so that's the one we know, and that's the part which will make a lot of mess, let's say, right? Because I mean, that's highly nonlinear. If you choose capital F to be something a bit weird, of course, everything will be complicated, and the rho as well, right? I mean, you can play with all these parameters. So xi are here they are nuclei. Rho I does what rho bar I what as I said, the cumulative effect of the atom placed at xi on the electronic clouds, right, related to other atoms, and F is the energy needed to embed an atom at position xi in the host electron gas. Okay, so that's very rarely you need all these things. So as the advantages of this system, of this way to write the energy, is that you can fit, I mean, you can choose a parameter to fit with experimental values, of course, and you can also easily implement and compute all these things because it's not difficult. It's basically two-body interaction with some, I mean, functional capital F here, which will play a role, of course, but computationally speaking, it's not that difficult. Okay, so now I'm going to the lattice case. In the lattice case, so if you consider a lattice, which is this kind of sum, right? And U1, UD is the basis of RD, right? And so you choose your function such that, okay, so here rho will be always positive, so don't worry, you can choose rho even not positive. In reality, it doesn't change anything for the computation I will show you. And you choose functions that are continuous, and rho and phi are integrable at infinity in the sense that when I will compute this sum here, of course, I want to take a limit, an average limit. So I want everything to be defined correctly. So now I take the energy of a piece of my lattice on a ball of radius r, and I divide by the number of points, and I take the limit as r goes to infinity. Then when I do this averaging, I obtain a new energy, which I will call EF of L. L is the lattice, and that will be given by two terms. The first term being capital F, so the embedded function of the electron energy plus the two-body energy, right? And my notation will be always the same. So E of small f or phi or rho, that will be this kind of sum, right? So which is absolutely convergent. There will be no problem at all here, right? So it's just a notation. So when you will see EF like that, it's just a sum on the lattice of with my interaction potential, small f. So the main question I want to address in this talk is the following. So given this function, what is the lattice minimizing this energy? Right? Very simple. And physically, that the idea is what is the best candidate for being the solid state, right? So I'm not showing any crystallization result here because as we all know in this community, I mean, you consider just the phi part of the energy, it's already a mess to show some crystallization results. So of course, if you add this capital F rho, terms, that will be a disaster. I mean, it's for it's for the next decade. I don't know. Okay, so just to remind you what I will call lattices, and just for my notation, I will call LD the set of all the lattices in dimension D. Easy. If I fix the density, I will, as usual, fix the volume, the co-volume of my lattice. So the volume of the unit cell, right? So I will have a unit cell of volume fixed equal to V. So that will be LD of V. So as we know or not, but I'm very fast here. But using the reduction of quadratic forms, you can show that all these lattices belongs to a fundamental domain. where there is only one lattice. Of course, you have rotation, you can have rotation, and so on. So, but there is one fundamental domain where one lattice is unique. The lattices are unique. And in particular, LD, so this set of lattices can be viewed as a point of R at the power d plus 1/2. So R3 for d equal to 2, R6 for d equal to 3, right? So if you want to minimize an energy for d equal to 2 into 2D, you will have 3 parameters, but in dimension 3, you will have 6 parameters, which is already a bit difficult. But if you fix the energy, the density of the lattice, of course, you remove one. To that, right? So you just have to subtract one. That's quite. I mean, in dimension 2, we'll have R2, and in dimension 3, we'll have R5. But okay, R5 is already difficult to handle. Very good. The usual lattices, the triangular lattice that we all know, the square one that we, of course, all know, the simple cubic, the FCC, face-centered cubic, and the BCC, the body-centered cubic, right? The notation here, A2 for this triangular lattice, D3 for the FCC, and D3 star for the BCC, because they are both dual to each other. So that's very usual thing, right? And I will only talk about dimension 2 and 3. Of course, we can always go to dimension 8 and 24 if we are very excited about things that are not like, physically relevant in my case, in this case, but mathematically interesting. Okay, so now I want to talk about interaction potentials. So what are the profiles of the function I want to use, right? Now you had time to read the joke, so I can go to the next slide. Usually, what we choose, so what are chosen by physicists, for example, it was given by Barnett J. Smith in '88, is this kind of profile. So for phi, so the two-body interaction, that will be a decreasing increasing function, so that like the Lennard-Jones one. Capital F, so the embedded function would be something with a well, like that, right? And a rho would be something which is decreasing, okay? I mean, I will choose more things because, as a mathematicians, we want to play a bit with the toys and we want to try things, right? Otherwise, it's not funny. But at least I will cover these things at some point. Okay, so for the nuclei interaction phi, I will choose either inverse power law or Lennard-Jones type potential. So AR minus alpha minus BR minus beta, where alpha is larger than beta and always larger than D, such that everything is totally absolutely convergent, right? So this one we know is decreasing, but this one is with a well, so that's very classical. For the electronic density, two things that are decreasing, okay, Gaussian and inverse power law. Why not? You can choose whatever you want, but here it's we know that for the. I mean, I will show you some things with the Gaussian, but the good point with the inverse power law is that it's homogeneous, so you will use this homogeneity a lot to study this energy. And for the embedded function, there is this one, which is a universal building curve for metals. So basically, it's a decreasing, increasing function, and that's the one which fits with the reality, as I showed you before. Otherwise, you can choose like an inverse power law. Okay, so that's just for playing. There is no reason to choose this one. But in '84, Finis and Sinclair, they propose the same kind of model but with capital F equal to minus C square root of R. Right. Okay, it was also something that you can cover with what I'm going to talk about. So the important thing is, that all these potentials, they won't be truncated. So in reality, for physicists, in this model, they are truncating the function and they are playing with that, right? But in that case, really, you won't see any truncation. Of course, when I will do numerics at some point, of course, I will truncate it, but it's not going to be problematic. Okay, so let's just speak very, very briefly about the F equal to 0 case, right? So the F equal to 0 case, so yeah, okay, very good. Okay, sorry, I just fixed a technical issue. All right, so that's the case where you have just the phi, okay? So, okay, so so I will just treat dimension 2 and dimension 3, right? So what do we know? So we know in dimension 2, things about minimizing this kind of energy, right? So that's the energy of one lattice submitted to the potential small f, right? Okay, so, and we want to minimize at fixed density where V is fixed, or without any density fixed. So as we know that there is an universal optimality, but among lattices, that unfortunately we don't know what's going on for the periodic case, but it was shown by Montgomery in 1988 that the triangular lattice is a unique minimizer of this energy for the Gaussian, right? So that's a very important paper for if you are studying energy minimization among lattices. And so that means that at any scale, the triangular lattice is minimizing the Gaussian interaction, right? And that's true for any scale, so for any value of the parameter alpha here, right? And what does mean? That means in particular that it's true for any completely monotone function. And I just repeat what completely monotone function here is that it's a positive decreasing convex function with alternation of sign for the derivative. And it's also the equivalently by the Bernstein theorem, the Laplace transform of a positive measure, positive Borel measure. Okay. An example is the inverse power law. So if you take the inverse power law r minus alpha, it's of course completely monotone because you can do that. It's easy to do. We know that for a while. And corresponding function, the corresponding lattice energy, sorry, is the Epstein zeta function, right? That I define here. So the Epstein zeta function is just the sum of 1 over norm at the power alpha, right? These bars are just here to say that it's a norm, right? And so with Mircea Petraki, a few years ago, we exhibit an example of function that seems to have the triangular lattice as a minimizer, but which is not completely monotone. But at least, I mean, it's completely monotone until k equal to 4. So it's alternation. There is an alternation of sign for the derivative, but not at infinity, as it is said in the definition of completely monotone. So the class of function for which this theorem should be true is a bit larger, of course. I mean, that's what we expect. And Cohen Kumar, they conjecture that these things should all among periodic configuration. So not only among lattices, but among union of lattices, right? At fixed density. Very good. Okay, so that was for the inverse power law for the Gaussian case. Now for the Lennard-Jones case in dimension 2. What we know is that so this energy can be written in terms of Epstein zeta function. So okay, there is a power law for with alpha and a inverse power law with beta. Sorry. And okay, so what we know now is that there is optimality of the triangular lattice at high density. So there is a V naught which depends on the parameter, such that for all V smaller than this V naught, the triangular lattice with covolume V is a unique minimizer of the energy. So that we know. And there are some recent general results that I obtained and that Lu and Wei obtained this year. Talking about this kind of thing. Also, we know that for chosen exponents, the global minimum of my energy among all the lattices in dimension 2 is a triangular lattice. That's what we know. I didn't specify what chosen exponent means here, but you have an infinity number of exponents for which it is true. And also something important is that the shape, let's say the shape of the minimizer does not depend on A, B, alpha, and beta. I mean, if you fix, what I mean is that if you fix alpha and beta, it does not depend on A and B. Right? So meaning that if a minimizer, if you have a minimizer of the Lennard-Jones energy, that means that if you take in L0 to have density 1, it is a minimizer of this funny energy, which is here, which is just a quotient of Epstein zeta function with this parameter alpha and beta. So here there is no A and there is no B, but that will be the same minimizer for any alpha and beta fixed, whatever A and B are. So you can play with A and B as you want. And there is a phase transition for the minimizer at fixed density. So when V starts at 0 and goes to infinity, at the beginning, the minimizer at fixed density is triangular. That's what I explained at the beginning. Then it started to be rhombic, right? So rhombic means that it's not, triangular, but it's not square, but it's in between. Then it is square for a while, and then it's going to be rectangular, right? So that's the things that you can observe. At least, and Lu and Wei, they have a proof of that in a certain range of V. Okay. So that's quite a nice thing. So in dimension 3, it's a bit more difficult, of course. So I recalled what the lattice theta function, Epstein theta function, and FCC BCC lattices are. But so what we know right now, so maybe I will forget people, of course, as usual, but we have this result by Enola in 64, showing that these two lattices, BCC and FCC, are local minimizer for the Epstein theta function. So we know that they are local minimizer. You can see also in the literature, Delon, Rishkov, Gruber, and other people working on spherical design, showing this kind of things. We know, for a while, I think it was maybe before Sarnak and Strombergson, but anyway, in this paper about the height of the flat torus by Sarnak and Strombergson, that there is no optimizer in dimension 3, so there is no optimizer for the lattice theta function for all alpha. And the conjecture is that it is the FCC for alpha larger than 1 and the BCC for alpha smaller than 1, right, by duality. There is also a conjecture for the Epstein zeta function. Here I won't talk about S smaller than D, but for S larger than D, that should be the FCC lattice, which should be the global minimizer. That's what they conjecture. Yes, so what we show with Mircea, and that I also showed the second part, that we show the local optimality of D3, right? Again, and the fact, so that's for the lattice theta function, sorry. And we also show that D3, so the FCC lattice, is a saddle point for small parameters, showing exactly that they cannot be both minimizer for the theta function for small parameter or large parameters, both at the same time. There is one which is minimizer, the other one is the saddle point. So it's a bit more messy, and we don't have a lot of things in dimension 3. And for the Lennard-Jones case, there is some high density minimality of the BCC and FCC lattices. So that's just, a consequence for the, of the local optimality for the Epstein zeta function. We also have this, okay, that's for any density, any dimension. So the same thing, that you have this, the fact that the shape does not depend on A and B. And recently with Samaj and Travnik, we did a numerical study showing that in the periodic case for alpha minus beta small, the FCC lattice should be minimizer, but when alpha and beta, the difference is large enough, that should be the HCP, which is depicted here, the hexagonal close packing. But in the lattice case, that the FCC should be the global minimizer, whatever alpha and beta is. That seems to be true. And you have also a phase transition at fixed density when the co-volume increase from FCC to the simple hexagonal lattice, which is depicted here, and more elongated, exactly as you have a rectangular lattice, which was more and more elongated as V increases, right? So that's just, but that's okay. That's just a bit of literature and some reminders about all these things. Very good. Okay. Okay, so now I want to talk, before the giving some theoretical result, I want to show different scales of the embedded atom model. And as before, I waited a bit for you to see the joke, because I put a lot of scales under that. Anyway, so you have two parts for the energy. You have the F rho part, which is the F of E of rho, right? So the embedded functions of the energy of the electron density plus the two body parts, right? You have two things, and for both things you have different scales, optimal scaling, right? So meaning what? Meaning that you want to delete L, so your lattice, and you want to find which is by lambda, and we want to choose the optimal lambda, right? So what is the best for this one, the first one, what is the best for the second one, and what is the best for the total energy, right? We have three things. So what I will call lambda LF, that will be for the whole energy, because you have this F here, right? Which is exactly the set of these three function F, rho, and phi. So now you understand that this will be for the F rho part, the optimal scales. So that's the minimum of the energy among all the dilated of L. And the third one, it's for phi, right? Okay, so we have these three parameters. And the goal is to find the optimal lattice among all these dilation. So for the Lennard-Jones case, we already know what is the minimizer. So that will be this one. So actually, there is no A2 here, it's L, right? So because it depends only on L. But you have, you can compute it very easily. I mean, it's easy to compute because in the phi case, you just use homogeneity of the Epstein zeta function because it is written in terms of Epstein zeta function. And then it's like, first year computation, and it's super easy to do. And for the inverse power law, of course, there is no minimizer. So that's totally clear. Voilà. And for the F rho part of the energy, it's a bit more difficult because you have this capital F and this small rho, which plays two different roles, right? But of course, if capital F is strictly increasing or decreasing, it's not, and rho is assumed to be decreasing. I mean, it's going to zero, right? I mean, this lambda, and that will be your optimal. I mean, there is no optimal parameters to get so it's going to zero to get the lowest possible energy, or to plus affinity, right? So it's not this part is not very convenient part. But what we show with Manuel Friedrich and Uli Stefanelli is that if F is a single minimum potential, exactly as I depicted here, right? And rho is positive, strictly decreasing, and absolutely summable, such that everything is defined, then there is an optimal, of course, scaling. And that's extremely easy because it's F of E rho, and you just have to find the E rho of L, so the lambda L, let's say, which match the minimum of F, so which match exactly this value. So it's extremely easy to do. And so it exists, but it exists not uniquely, because you can choose for fixed L, there is a lambda L, right? But of course, you have an infinity number of, you have an infinity number of lattices, and for each lattice, there is a lambda L F rho, this lambda L F rho, which gives you the minimum of capital F, right? But that's important to understand that, because if you do that, you have to play, I mean, it's just a way to explain that we have to play with both energy, both terms of energy, and you at some point you can make them match to get the minimum of the energy, right? Okay, so there is a way to have the minimum here, which is given by this very easy energy. Very good. Very good, very good. Okay, so what are the theoretical results for the embedded atom model? Right. So that's the only result that we have with Manuel and Odyssey. So I will give you two results. The first one with rho, which will be R minus S, and phi, which will be a strictly decreasing function, but in the inverse power law, right? So in that case, so it's not a physically relevant case, but it's a mathematically interesting one. So the energy is given by capital F of the Epstein zeta function plus the Epstein zeta function of alpha, right? And you have alpha, which is assumed to be larger than S, right? Because if it's not the case, there won't be a minimizer. Okay, so now you have some ugly technical assumptions that are necessary. So from this capital F and alpha S, data, you make this function g, which is r1 minus alpha over sf prime, and h, which is given by that, right? And you assume three things. The first one is that g will be increasing in the part where f prime is negative, right? So when f is decreasing, g will be strictly increasing in this part. You assume that g of I, so this f prime will be all the negative numbers. And you assume that when you compose h and g here, the function ng minus 1, sorry, this function will be strictly decreasing on the negative real number because of that, right? Okay. And okay, so they are the assumption. Okay, so they are technical. I mean, they are here just to have something nice that I will explain in the next slide. So don't worry. This is a key point because I will show you in a moment what's going on. But okay, so everything will be related to the Lennard-Jones potential F, which is defined by R minus alpha minus R minus S, right? So there is a Lennard-Jones potential that you can make with these two guys. Okay. So that's a Lennard-Jones potential I will talk about. Okay, now I show you the result. So I just recalled what are the functions. The function capital F is just C1 and satisfy all the assumptions of the previous slide. Small f is Lennard-Jones energy, and I just the Lennard-Jones potential, and I just recall what the Lennard-Jones energy is here, right? Okay, so the result we obtain is the following. Under all these assumptions, you have two things that exist. The first one is the optimal scaling for the wall energy. So when you do the dilation of L, okay, at fixed L, there is a unique lambda L which exists. Actually, that's a unique one. And there is the same exists for the Lennard-Jones case. So the optimal scaling when you fix capital L exists. Okay, so that we know. And we have three equivalent statements. The first one is that LD, so that's a lattice. Okay, so these things are equivalent. So if LD is a unique minimizer of E star, the E star of the Lennard-Jones energy, this is equivalent, as we know, with the third point, the fact that with this scaling, with this particular LD, that's a unique minimizer of the total energy EF. Okay, the Lennard-Jones energy, the global minimizer of the Lennard-Jones energy. So these two things that we already know, right? But this is equivalent with the fact that this LD is that's exactly the good shape. So meaning that this lambda LDF, which is the optimal scaling for LD, times the lattice LD is a unique minimizer of our wall energy. So basically, what that means that the shape of the minimizer for the Lennard-Jones and for this embedded atom energy is the same. So if it's triangular in one case, it will be triangular in the other case. You see FCC in one case, FCC in the other case, right? That's only what it said. And as I told you, the assumptions, very complicated assumption I showed you before, just means that when you dilate, so if you fix L, so this is a lattice L, and you make some dilation with lambda, the energy will be decreasing, increasing, right? And so there will be a minimum which is given by this scaling, right? And also the second thing is that when you compute the critical point, so with lambda, you obtain a certain equation. So you just have to compute, blah, blah, blah. You compute, you compute. So yes, that's yeah. So you compute the derivative of the energy, which is here with respect to lambda, you obtain something, and then you put that in the energy of itself, and you would get H composed with J minus 1 of this E star with a minus 1 here. And that's why you have equivalence of these two things. The fact that you have the unique minimizer for E star and the unique minimizer for EF, right? So that's the point. So the proof is not difficult to read. There is just a lot of parameters, and that's only that can be scary, but otherwise it's easy. Okay, so now, what are the applications for that? I mean, since we know what are the minimizer in dimension 2 for the Lennard-Jones case, right, is for some parameters, for some value of the parameters, we can define these parameters, and we can show that the embedded atom energy is minimized by a triangular lattice, right? Okay, very good. And what are the embedded function capital F satisfying these ugly assumptions? They are the single minimal, I mean, the one I depicted at the beginning, so the universal building curve. The Finis-Sinclair energy is also satisfy also these things, minus log R and R minus T, right? So that's exactly the one I wanted. So that's something which is a bit more general, but at least it's applied for this usual function. Very good. So now we can do the same with Lennard-Jones phi. So now phi is already something a bit more physically relevant, right? So phi is something which is decreasing and increasing. Rho is still decreasing, okay? And what we want here, so for this first result, we suppose that capital F is exactly this universal bending curve that I depicted before, right? So if you do that, as I told you, you have two energies, this first energy and this second energy, which is the Lennard-Jones one. There is one optimal scaling for this one. There is one optimal scaling for this one. And actually, it's so we know that for this one, the optimal scaling, actually the minimal value for this part, the capital F part, is achieved for any lattice you want once you have chosen the good scaling, right? But the one on the right, the minimizer is a triangular lattice for a lot of parameters that we know, right? And so that's kind of good, because now if I choose alpha and beta such that I know that I have a triangular lattice which is minimizing my energy here, I can just, what I can do is I can just choose the scaling parameters to be the same here and here for these two functions, and then I will have a triangular lattice which will be a minimizer for the whole energy, right? So it's a stupid thing, because I have two things that they don't see each other, but I will just play a bit with the scaling parameters for both, right? So that's what I wrote here. So given parameters such that E phi, so for the Lennard-Jones energy, is minimized by the triangular lattice, the corresponding triangular lattice. Now you can find actually A and B, so this parameter A and B, such that the scaling parameter for the right and the left will be the same, meaning that the minimizer of the energy will be triangular, right? And that's exactly what I explained here. The idea is just to compute both scaling and you win. So that's that's a stupid easy, but that's a stupid idea that works. But yeah, that's kind of a bit too easy. So there is a second thing where you have to do the same assumption. So you have to assume the same thing as in the inverse power law case, these ugly assumptions with H and G. And you assume also that F is convex, right? Convexity of capital F, C2 and convex. If you do that, you have the same result as in the inverse power law case. So the minimizer of the Lennard-Jones will be the same as the minimizer of the embedded atom model, right? So there is no difference between these two things. And the idea how to do that, so here there is a bit something that I didn't tell you, but it's my R minus S, but that's the same R minus S, so there is the same tail for rho and phi, right? And that's a very important thing, because in that case, the total energy can be written in terms of Epstein zeta function that way. But you see there is this zeta L of S here and here. So basically, you can write everything with a certain function of zeta L of S plus zeta L of alpha, and then you go back to the previous case, and then you win. It's easy to do. Right. But at least you have to, you have to choose F to be C2 to have this curve again, to have a minimal energy, and everything will work perfectly here. Otherwise, it's not going to work because of this shape of this new function F tilde, which is a bit different. But okay, it works, and you're happy. So basically, what you see here is that okay, if you know something for the Lennard-Jones, you know something for this embedded atom model, right? So it's not very surprising. We have the same minimizer, but at least it's nice. So as I told you before, so if one is, in dimension 2, basically, I mean, we know that for triangular lattice, that's the shape you will get, right, for the embedded atom model. And of course, here, you have to be convex and C2. Okay, at least the convexity is a bit of problem. So the application you get is for R log R, but for capital F equal to R log R. But that's the usual one that you see in the literature. So you are happy and you say, okay, physically speaking, I'm still on the good path, and everything works well. Okay, so I will just show you now some numerical investigation that I did, that we did actually with Manuel and Ulysses. We did that for these cases I told you before, but I mean, before I told you that I can take the Lennard-Jones and I can take rho, but normally the power here, which is the smallest for the Lennard-Jones and the one for rho should be the same, right? But here I mean, since I'm doing numerical amplification, I can do everything I want. So what you see is that for S larger than 5.14, the global minimizer seems to be triangular. That's what you know for S equal to 6, but not for other parameters. And for S smaller than this 5.14, there is no global minimizer. Okay, that's what you see. And and you can compare the square and the triangular lattice. And for S larger than 5 something, the triangular lattice wins, and otherwise it's the square lattice that wins, right? In the case where you have no global minimizer. So that's what you see in these pictures. So the way you do is you parameterize your lattice as a point in the fundamental domain D, where here that's the triangular lattice, and here that's the Z2 lattice, the square lattice. And so here you see that this point actually, which is black, which is the minimum, is the triangular lattice. That's for 6. Here that you see that for 5.15, you still have the triangular lattice, which is minimum, but you have a black part, which is here. But then when you get at 5007, you are not a minimizer anymore. It seems maybe that 1 is the saddle point or thing, but actually the minimizer has to be degenerate. So you have to go up and to degenerate the lattice to be minimal. So you can do the same with the Gaussian, right? So you take rho to be a Gaussian function. You would still take the classical Lennard-Jones energy. And then you have something a bit different, a bit more interesting. So delta is the parameter of your Gaussian, and for delta sufficiently large, so larger than 104, the minimizer seems to be triangular. But for delta, smaller than this value, the global minimizer seems to move increasingly on the y-axis, meaning that you have something which is rectangular and going to be degenerate. But that's a global minimum, not a minimum at fixed density. So with the Gaussian case, you can create a minimizer which is not a square or not a triangular lattice, right? And if you compare, if lambda is smaller than lambda 0, that's the square lattice which wins, right? But does that mean that the square lattice is a minimizer? So that's what you see here. So so for 2, for example, you have a minimizer which is a triangular lattice. Then it started to go on the left side of the fundamental domain here, which means that's a rectangular lattice, and the point goes up and up and up, right? So that's a way to construct a new kind of ground state in dimension 2, which is not the usual one, okay? And by using very, very easy tools. You can do the same in dimension 3. So basically, I just took the same thing in dimension 3, right? And so in that case, I just compare the cubic, the BCC, and the FCC, right? And so in that case, you have threshold value, such that you change the order of your minimizer, let's say, of the value of the minimal energy for the cubic BCC and FCC. So here it's a cubic, which is the smallest one for S between 3 and S naught, which is 5, right? So you have something which is cubic lattice, which is the best among the cubic lattices. And then you start to change. So you see there is exchange after S0 between 0 and S1, and then exchange again, right? So you see something a bit funny, which depends on the parameter S. And yeah, so maybe, I don't know if there is a simple cubic phase as a ground state here, but we have some hope thanks to this numerics. And that's what you see, right? So the black curve is a simple cubic, the red curve is the FCC, and the BCC is the blue curve, right? And so you see what's going on after for sufficiently large S. And for small s, you see that everything is like mixing together, right? And you see the same actually when you replace rho by a Gaussian. So here rho was an inverse power law with S, but with a Gaussian, it's the same trick, right? So that's interesting because you can get something which is non-usual for this energy compared to the F equal to 0 case, right? And so that will be all for me. But I mean, this work, now we have undergoing work with Stefano Almi and Alex on dilute systems. So you consider the same kind of energy, but with continuous things, and then will have equilibrium measures, Boltzmann inequalities, first order asymptotics when the number of points goes to infinity. All these things that we are doing, and that almost done for most of them. And that's also quite kind of exciting to have a new model and to have new ground state, and then you can tune capital F and change a bit the minimizer. That's I think it's kind of exciting, a bit different. So thanks a lot for your attention. And if you have any questions, go ahead.
Thank you, Laurent. This nice talk, and also for showing us what the rest of your room looks like. So are there any questions to the speaker? Okay, maybe while people are thinking about questions, I'll ask just this sort of maybe tangential thing. So about this power law for rho, right? So how physical is it, right? So it seems that exponential rho is a better, I don't know, physics. So you have looked at all this literature. Do people use power law rho? Is this common?
Everything is truncated in the literature. So I mean, but yeah, no. To be honest, no, it's not common. To be honest, I mean, okay, so it's really a technical problem, because when you write the energy, so basically here, for example, so really the idea is to use. So the key point of the paper is to use this different scales, right? And if you don't use a power law, you are not able to use the scale properly here. So
of course, yeah.
So it's really more difficult. I mean, I think it's doable, but you have to take into consideration. I mean, when you do the computation here with lambda and you delete your lattice, everything is simple. It's not extremely simple, but it's simpler than in the Gaussian case or exponential case, right? That's really why we did that, and it's But I agree with you. I mean, the best way would be the best physical way that would be to put an exponential instead of a power law here. And that's why we did some numerics after that. I mean, that's of course, because we were not able to do it by hand.
Yeah, I see.
But yeah, that's,
okay, maybe I'll just. So you mentioned truncations, and then earlier in the talk and right now. So what about that truncation? Can you tell us something more? What kind of truncation do people use? Is it radial truncation?
Yeah,
use neighbor truncation, right? So what do they do?
Exactly. So usually, so I see where it is. Where I explained that. Yes. Okay. So usually, what people are doing is that they are, cutting. I mean, they are only considering nearest neighbors. I mean, that's the point. I mean, when you see the literature, for example, for the FCC, I mean, for metals, for example, what you expect is to see some FCC or BCC lattices, and they are only, considering metals. I mean, so okay. So when you look at the literature, what people are really doing, physicists are really doing, they are saying, okay, we already know what is the structure. And now we want to find the parameters such that what we find match with the energies or with the values we experimentally obtain, right? So that's what they do. So when you look at the model, they just consider nearest neighbors, and so everything is truncated very, roughly at one, basically. And so yeah, that's why when we started to do that, we thought, okay, it's really the optimal point configuration, philosophy to say, okay, we are not going to do that. But okay, so what you can imagine, so to jump on your question, would be to consider truncation everywhere and to do some Heitman-Radin perturbation again, and to show some crystallization results, right, basically. So there is some room for that, because for phi to be like art sphere potential plus infinity minus 1 0, you can consider art sphere potential, and then you can consider something else here, right? So you can perturb a bit things and maybe show some crystallization results on the triangular lattice or on something else. But yeah, so that's what I know about truncation. So I mean, I wrote it here because of course this community knows that we are not truncating the potential when you play with this kind of things. But I thought it was important to mention it. Yeah.
Mm-hmm. Thanks. I see. Right. Any more questions? Okay, maybe let's try disabling the recording and see if people are willing to ask a question off the record. So hopefully this will open space.
No, I don't think that it will change anything. People are not